Hello, am I audible?
Yes, ma'am.
Okay. So let's wait another 3 minutes. We'll start at 3:35. Okay, because 28 have joined only. Okay, so 40 have joined so far. So can you start now? You all are here, right?
Yes, ma'am.
Okay. Okay, so you can see the PPT now, right? Is it visible?
Yes, ma'am.
Okay. Okay, so last day we discussed some basics of illumination engineering, like what is electromagnetic radiation, the visible wavelengths, the black body and black body laws, etc. These were few radiators and one numerical problem was there. So then we discussed the spectral power distribution curve of any radiator. So if you remember what is a Spd curve, if if we plot the radiation from any light source over the radiant power and wavelength, then we can get the pictorial representation of the nature of that radiation or light. So how the white light, it's comprised of all the 7 colors or not? What is the total amount of radiation? Which color is more prominent? Which one is less present? Like this. So these are different type of SPD curve of different light source that we that are used in commercial applications or residential application, etc. This is for LED. Um, so this is another way of presentation. Here I have shown the spectrum of a white light. The visible part, you know that, sorry, it's from 380 nanometer to 780 nanometer. Below 380, it's called UV. Above 780, it's called IR. I'm audible, right? The voice is clear?
Yes, ma'am.
Okay. So you know the principle of prism. If the white light passes through the prism, it will get dispersed and we can see the colors present in the spectrum of that respective light. All the 7 colors may be present, may not be present, depending upon the type of the source. But here all the 7 colors are shown here. You can see violet, indigo, blue, green, yellow, orange, red, depending upon the angle of dispersion, right? So the white light, the incoming light is white. And if you look from this side, you can see all the monochromatic colors. So you can see the violet to red, whatever is present. So if you remember that lab, if you look at the constant deviation spectrometer, you can see the colors present in the light of that source. So this is the incoming ray, and if you look through this side, you can see the respective colors. And so this is an example of a discharge light source. You can see 400 nanometer to somewhere 650 nanometer or more is visible here. So these lines are due to the light from that source. You can see violet, blue, green, yellow, red, etc. So this is called the one-dimensional chromatic presentation, because you can see only the colors present in that respective light, not the amount of radiation. From this figure, we cannot understand that how much blue is emitting or how much red is emitting. We cannot see that. From here, we can get an idea that yes, the yellow is prominent, some more lines in the blue region, and it's not continuous. There are some lines only, some discrete lines only. But if you see this continuous spectrum, you can see that all the colors are overlapping each other. From red to violet, all the colors are present, but you cannot differentiate them separately. But again, the y-axis is missing here, means the amount of radiation is missing here. So this is called one-dimensional chromatic presentation. We can also represent the spectrum in 2-dimensional, which is the SPD plot. So in 2-dimensional, you can understand that we have the wavelength as well as the amount of power, right? Amount of power means, suppose for a 100-watt filament lamp, we know that incoming power is 100 watt. So from the output, suppose we are getting 40 watt radiant power. So this is that power for each wavelength. So that's why it's called relative spectral power. And it is a normalized curve, so that's why with respect to 100, all the other colors are presented here. So from this curve, you can understand that the maximum radiation will be in this region. It's 100. With respect to this 100, we will get some 60% red, some 60% blue, 80% of green, 70% of yellow, like that. So this is the 2-dimensional presentation. We can get an idea about the colors as well as the amount of radiation. Okay. So this spectral power distribution can be either continuous or discrete. This is a continuous spectrum and this is a discrete or line spectrum. So for example, you can see for incandescent lamp, it's a continuous spectrum. For daylight, from sunlight, it's again continuous. Mercury fluorescent, it's almost discrete. Low pressure sodium vapor, it's only a line, so it's a line spectrum. For high pressure sodium, somewhere it's line and somewhere it's continuous. So this is a mixed kind of spectra. For metal halide, again, it's a mixed kind of spectra. Cool white, warm white LED. This may be continuous or this may be mixed depending upon the type of the LED or depending upon the type of the light generation. But for the thermal radiator, like incandescent or sun, these are all continuous spectrum. Okay. Sorry. So from the Spd curve, we can get idea about the nature of the emitted energy plotted over a range of wavelength. The thermal radiators give continuous Spd, gas discharge lamps show line spectrum or discontinuous spectrum. So it provides information about how much portion is visible and total amount of radiation. So what do you mean by this? How much portion is visible? Suppose from a fluorescent tube, uh, mercury vapor, we know there are UV radiation, lot of UV radiation are there, but the UV part is not visible. So among the total amount of radiation, how much we can see? So that is how much portion is visible and the total amount of radiation. Okay. So any question up to this? Anyone?
No.
Okay. Just a second. Okay, so if Spd is clear, then we can move on to the next point, which is spectral response of human eye. So before going into the discussion of lighting parameters, we need to discuss how we can see or how we can perceive the light. So that's why we have to discuss the spectral response of human eye. You know that in the entire just a second. These are different kind of electromagnetic spectrum. There are X-ray, gamma ray, radio wave, microwave, etc. But we can see only the visible part because our eye is responsible to only this 380 nanometer to 780 nanometer. Beyond that, our eye cannot detect the light. Okay, so if it's below 380 or above 780, our eye cannot detect that particular radiation. So that's why that's not visible to us. So why it cannot detect below 380 or above 780? That's because of the light responsive cell of our eye, which is cone and rod. You know that there are two type of photoreceptor in our eyes. One is called cone cell, another is rod cell. So due to the presence of this cone and rods in our retina, we can detect the light. Cones and rods are responsive only in between to 380 to 780 nanometer. But in between this 380 to 780 nanometer, it is not equally sensitive to all the wavelengths. The responsivity or the sensitivity of these two cells are different for different wavelengths. That means I want to say that suppose we have same amount of blue radiation, we have same amount of yellow radiation, but we will see the yellow more. We will see less amount of blue because our eye can perceive more amount of yellow light than the blue light. That is the property of this eye detectors. Okay, so here you will see how the eye is responsive to this different wavelengths from 380 to 780 nanometer. So as I told that there are two receptors, one is cone and another is rod. So you know about the sensor and detectors, right? You have studied about sensors. So these are just like two sensors present in our eyes, which can detect this particular wavelength. So cones are responsible for light adaptive vision. That means when our eye is subjected to a more amount of light level, then the cones are functioning, and that vision is called photopic vision. And that particular spectral response is called V lambda. Whereas when the light level is low, when it's dark, then the rod cells are functioning, and that response of rods is called V dash lambda. So you can see two lines here. One is for V lambda, this one, and this is for V dash lambda. And in the background, you can see the colors. Okay. So if you see V lambda, it's from 380 to 780. The peak is at 555 nanometer. The value is somewhere here, it's 683. For the V dash lambda, you can see this is from 380 to 780 again. The peak is at 507 nanometer and the value is 1700. Okay. So this V lambda, this is the response function of cone cell. Means how our eye can see under sufficient light level. The peak is at 507 nanometer, which is 555 nanometer, which is in the yellow region. We know that we can see yellow more bright. We can perceive more yellow light, right? That's because the peak of the cone cell is at 555 nanometer at the yellow region. So that's why we can perceive more amount of yellow light as compared to the other colors. Whereas if you see the rod function or V dash lambda, you can see the peak is at 507 nanometer, which is in the bluish region. So that's why in dark, we can perceive more blue light than the other colors. So the cone peak is 683 lumen per watt. What is lumen per watt? That we will discuss later. But just for now, what is the input power? And lumen is the total light. So this is how much input power we are giving to the lamp, and this is how much light we are getting from the lamp. So this peak is 683 lumen per watt at 555 nanometer. For rod cell, the peak is at 507 nanometer. The value is 1699 lumen per watt. So this is how our eye can see according to the cone function. Okay. This is how I can see according to the rod cell. So that means you can understand that if we get any light from any source which is in this region, if any radiation is in this region, that light we cannot see, that light we cannot perceive, because this is beyond our eye capability, right? Our eye cannot detect this part, right? So even if there is some light coming from the source, our eye cannot detect that amount of radiation. So how much light we are seeing from the light source, that depends on the eye functions too, how much we are detecting, right? So that totally depends upon this V lambda function and the V dash lambda function. So depending upon that, there are three kinds of vision. One is photopic, then scotopic, then mesopic vision. So when the response is dominated by the cone cell, that is called photopic vision. And here we can see fine image as well as the color, means we can identify what the colors under photopic vision. And the spectral luminous efficiency function is V lambda. Now, I am telling that higher amount of light level, a high light level. So how to quantify that high level? Here its luminance is more than 5 candela per meter square. What is luminance? That we will learn later. But for now, when some light level luminance is more than 5 candela per meter square, then the vision is photopic vision. We can see the details of the image and we can identify the colors. That type of vision is called photopic vision. The cones are responsible for this kind of vision, and the function is called V lambda, the spectral luminous efficiency function. But when that light level is low or dark, or when it is less than 0.005 candela per meter square, then the rod cells are functioning, and it is called scotopic vision, and it functions under dim light and we cannot identify the colors. For example, under moonlight, you can see some object, but you cannot identify the colors of the object, right? So that is an example of scotopic vision. And when the vision is in between this photopic and scotopic, means when the in between 0.005 and 5, we call that as mesopic vision. And both cone and rods are responsive for this kind of vision. And there is no such specific luminous efficiency function, but it comprised of the V lambda and V dash lambda. So any question after this? Anyone?
No, ma'am.
No না
ম্যাম
এখানে
পিক
কোশ্চেন থাকবে হ্যাঁ বলো
ম্যাম পিক ভ্যালু যেটা বলছেন ওই এফিকেসিতে সেটা তো ডিফারেন্ট ল্যাম্পের জন্য ডিফারেন্ট হতেই পারে।
না ডিফারেন্ট হবে না, বিকজ এটা আমাদের চোখের প্রপার্টি, মানে আমার চোখে এটাই দেখবে। তো ল্যাম্প আলাদা হলেও আমার চোখ তো আর চেঞ্জ হবে না, তো এটা হচ্ছে চোখের প্রপার্টি। এবার ল্যাম্প যেরকম থাকবে সেটার সাথে এটাকে কম্প্রাইজড করে তারপর আমি কতটা দেখতে পাবো। this is the property of the human eye. It does not depend on the lamp.
ওকে ম্যাম।
Okay, আর কেউ? Anything else? সবাই বুঝতে পেরে গেছো? আরো কিছু কোশ্চেন নেই? Okay, so next is as I told that for photopic vision we have V lambda, for scotopic vision we have V dash lambda, but for mesopic vision both V lambda and V dash lambda. If it's more light, if it's towards the photopic vision, V lambda is V lambda is more prominent there, and if it's towards the dark vision or scotopic vision, then V lambda will be dominating. So you can see one function, no details is required for your syllabus, but just for your information, you can see the V mesopic lambda. This is the luminous efficiency function of mesopic vision. This is not fixed, but rather depends on the V lambda and V dash lambda. This is the normalized curve. The black one is for photopic. You can see the peak is at 555 nanometer or yellowish region, and for rod cell it's at 507 nanometer, and the peak is 1700 lumen per watt. This is normalized function. This is the actual one. This scotopic and photopic. Okay, so this is just an example that under bright sunlight, it's photopic vision. When it's some raining, the light level drops, the luminance values is like 100 candela per meter square. It's again photopic vision. Under street lights, or under night light level, it's between 0.005 to 1 candela per meter square. So then it's mesopic vision. Under moonlight, it's less than 0.005, so that is scotopic vision. So for photopic vision, we have cone, we can perceive the colors. Under scotopic vision, we can identify the object, but not the colors. In case of mesopic vision, it's comprised of both cone and rod, and it lies between this 0.005 to 5 candela per meter square. So when we are seeing under bright light level, then our cone cells are functioning. Our eye response will be like V lambda. And when it's less than 0.005, our eye response will be like V dash lambda. This is the same photograph under photopic vision and under scotopic vision. Okay. Here for third one, you can see the scotopic, mesopic, and photopic. For scotopic, we have rod. For photopic, we have cone. For mesopic, we have both. So when the light level is increasing, the amount of cone cell participating in vision is increasing. After 5 candela, it's all the cones. And when the light level is decreasing, the rod cells are increasing. And below 0.005, it's all rod cell. In between that, we have the mesopic vision. Okay. This is another representation. This is V dash lambda or rod response. This is V lambda or for photopic vision. And as I told, there is no such specific V mesh, but it depends on V and V test. So that's why for different values, we have different kind of V mesh. Okay. So CI standard observer. Now the fact is that although I am telling that this is the function of human eye, but all of us don't have the same kind of eye, right? Sober eye power is not same. Somewhere for someone it may be less or more than 555. Someone can see more or less than the others. So that's why CIE or the Commission or International Commission on Illumination, like for electrical, all of you have heard about IEEE. Similarly, in lighting, we call it International Commission of Illumination, the international body or the CIE. They have established the standard observer that from 380 to 780, these are the values of response. So whatever we, this is the standard photopic observer. Okay. So কারো এরকম হতে পারে, কারো একটু different হতে পারে, but CI have specified the different values. Different values means for lambda and for V lambda. CI has specified the values for the standard observer. So whatever be the values for different individuals, there is some standard, and there the respective values of lambda for each V lambda are specified. That is called the standard photopic observer. এগুলো different year এর publication আছে, like 94, 1988, 1951, like that. Okay. So next we will go to the terms used in illumination or the parameters that we used in illumination. But before that, any question? Anyone?
ম্যাম অ্যাডাপটিভ কোএফিশিয়েন্ট যেটা আছে না, মানে ওটার ফিজিক্যাল সিগনিফিকেন্স কি?
ফিজিক্যাল সিগনিফিকেন্স হচ্ছে ধরো ওই যে বললাম হাই লাইট লেভেল, মানে এক 5 এর উপরে যখনই যাচ্ছে সেটা হচ্ছে ফোটোপিক ভিশন। ধরো তুমি ব্রাইট সানলাইট 10⁴ জল পড়ছে এরকম 100 ক্যান্ডেলা পার মিটার স্কয়ার, লাইক দ্যাট। বা আমাদের বাড়িতে এখন আমরা বসে আছি 10 to 15 ক্যান্ডেলা পার মিটার স্কয়ার, লাইক দ্যাট। So these are the different luminance values. So when the luminance values is decreasing towards the dark type, so then the cone functioning is reducing. Okay, and when the light level is increasing from low to high, then the functioning of rod is increasing. So the value of M at scotopic vision is 0. The value of M at photopic vision is 1. M is adaptation coefficient. The value is from 0 to 1. So when all the cone cells are functioning, when it is completely photopic vision, the value of adaptation coefficient is 1. And when it's rod cell, scotopic vision, it's 0. So in between 0 to 1, we have the mesopic values. When the light is increasing, participation of cone is increasing, it's the value of M is also increasing from 0 to 1. When the light is decreasing from high to low, the participation of rod is increasing, then M will be from 1 to 0. Here both rod and cone are same, scotopic and photopic are same. Here it is 0.5. At this point, the value of adaptation coefficient is 0.5. Means it's half scotopic and then half photopic. Clear?
Okay.
So depending upon the adaptation coefficient, we can calculate the mesopic function. You can see it's m v lambda plus 1 minus m v dash lambda. M is for normalizing, just forget about this m. So it's v mesopic lambda equal to m v lambda plus 1 minus m v dash lambda. So you can see when the value of m is 1, the v mesh will be v lambda plus 0. So it's completely photopic. When the value of m is 0, this part is 0, here it will be v dash lambda. So m for between 0 to 1, all other will be mesopic. Otherwise, for 0 it's photopic vision, for 1 it's photopic vision. Okay, and this is capital M for normalizing the function, like to attain the maximum value of 1. Like comparison এর জন্য যেরকম এটা হচ্ছে কি actual curve, this is not the normalized function. You can see the actual peak values like 1700 or 683, but the same curves are here. This is the normalized function, the peak is 1. So the normalized function, this one, you can see the blue for value of m is 0, scotopic. The red one, value of m is 1, it's photopic. For all the others, value of m, a few examples are given. So other than the blue or red, all are different kind of mesopic vision. Okay. আর কেউ কিছু? Anyone else? বাকি কারো কিছু কোশ্চেন নেই? অগ্নিপ, সম্বিত, আকাশ, তোমাদের কিছু কোশ্চেন নেই? সৌভিক?
No, ma'am.
Okay. Okay, so next, different parameters used in illumination. How to quantify? Like we use voltage, current, frequency, power. Similarly, what are the parameters used in lighting? So you can see few names here: luminous energy, gradient flux, luminous flux, efficacy, etc. So we'll discuss one by one. So luminous energy, this is the visually evaluated radiant energy traveling in the form of electromagnetic wave. Just a minute. Let's start with the this example. We have some input power to any lamp. Suppose we have one tungsten filament lamp at our house. We are providing some electrical power, so that we call the electrical power in watt, right? So after that, after glowing of that lamp, whether it's thermal radiator, whether it's gas discharge, whether it's LED, whatever, we will get some output power, output radiant power. This is called output radiant power. This is also we express in watt. So this is the input watt electrical power. This is the radiant power or the radiant power in watt. Now among this total amount of radiant power, we can see only in between to 380 to 780. So that is called light or luminous flux. We call it lumen or luminous flux. So you remember that the input power, electrical power in watt, the output we get from any lamp, total amount of output that is called the radiant power. It is also expressed in watt. And out of this total amount of radiant power, uh, we can see a certain amount of radiation that is called luminous flux or lumen. So let's start with the luminous energy. So the electrical energy, that is watt second, right? So the visible part, the visually evaluated radiant energy traveling in the form of electromagnetic wave, that is the luminous energy. Okay, so the input যেরকম ইলেকট্রিক্যাল এনার্জি হচ্ছে সেরকম আমরা কতটা ভিজিবল আউটপুটে পাচ্ছি, দ্যাট ইজ দ্য লুমিনাস এনার্জি অর লুমেন সেকেন্ড. Next was radiant flux. What is radiant flux? What you just see in the previous slide, the total amount of output that we are getting from the source or the rate of flow of energy emitted and is measured in watt. And what is spectral radiant flux? Spectral radiant flux is nothing but how much radiation we are getting from the light source at each wavelength. Like if you recall the SPD, this one, here we have seen that different output at different wavelength. So this is nothing but that radiant flux. And when we are plotting this radiant flux for each wavelength, we are calling that as spectral radiant flux. So the radiant flux or the emitted power at each wavelength, that is the spectral radiant flux. ইনপুটটাকে আমরা বলছি পাওয়ার, ইলেকট্রিক্যাল পাওয়ার, আউটপুটটাকে আমরা বলছি radiant flux, okay, or phi e. And spectral radiant flux, we phi e at each wavelength, phi e lambda. So the input is electrical power in watt, the output is also in watt. And this watt per nanometer for spectral radiant flux or for each wavelength. So the spectral radiant flux is phi e lambda, and for inter lambda you consider koro, you will get the total radiant flux or phi e. Is this okay? So the input is P or electrical power watt, the output is phi e. Anyone, any question? Yes or no? এটা একটু কনফিউজিং, সো দ্যাটস ওয়াই আই এম আস্কিং, মানে পরে গিয়ে সবগুলো একই লাগবে প্রথমবার শোনার পর. This one is okay, like right? Radiant flux.
Yes, ma'am.
Okay.
স্পেকট্রাল
হ্যাঁ বলো.
স্পেকট্রাল রেডিয়েন্ট ফ্লাক্সটা আরেকবার বলুন.
স্পেকট্রাল মানে ফর ইচ ওয়েভলেংথ, রেডিয়েন্ট ফ্লাক্স হচ্ছে টোটাল আমি কত আউটপুট পাচ্ছি, এবার ওই টোটাল আউটপুটটা ফর ইচ ওয়েভলেংথ যদি তুমি কনসিডার করো সেটা হচ্ছে স্পেকট্রাল রেডিয়েন্ট ফ্লাক্স. মানে in the entire course, whenever you will see the term spectral, that represent for each wavelength. Okay, মানে এই যে phi e আর phi e lambda, মানে suffix lambda আছে, for example what is phi e at 380 nanometer or 400 nanometer, 450 nanometer, like that, at a particular wavelength.
Okay.
Okay. It's a flux of radiant flux. So in this slide you can see radiant flux. The next slide called luminous flux. This one radiant flux, next one is luminous flux. So out of this total phi e, how much we can see or how much part is visible, that is called luminous flux. Okay, so the input was electrical power P in watt, the total output was radiant flux pi e in watt, and the visible part of this phi e is called luminous flux. Okay, so this is the time rate of flow of total luminous energy responsible for visual sensation. The unit is lumen. So you can see this radiation output. In x-axis we have the wavelength, y-axis ta dewa nei. This is again the radiant flux, the amount of radiation power. So suppose, for example, this is the radiation nature of any lamp. But whatever be the radiation from the lamp, we cannot use the total amount of power. For example, Nowadays we do not use the filament lamp because that is not energy efficient. Why not energy efficient? Because even after giving 100 watt, you can get a small amount of light at your house, right? So that's why that is not energy efficient. We cannot utilize more amount of electrical energy. Wastage time maximum. Why wastage is maximum? Because ওখান থেকে হিট বেশি হয়, যতটা না লাইট হয় তার থেকে বেশি হিট হয়ে যাচ্ছে। হিট মানে কি আইআর বেশি হচ্ছে ওখানে। The visible part is very less. Now that visible part depends upon our eye, যেটা আমরা আগে দেখলাম ভি ল্যামডা ফাংশন, রাইট? সো হোয়াট এভার বি দ্য আউটপুট, সেটাকে আমার ভি ল্যামডার সাথে ম্যাচ করতে হবে, রাইট? মানে বাকি রেডিয়েশন, এক্স রে, গামা রে, মাইক্রোওয়েভ, ইউভি, আইআর হয়তো লাভ নেই, যতটা আমি লাইট পাবো ওখান থেকে সেটাই আমার ইউজফুল পার্ট। So how to calculate that useful part? To multiply with the V lambda. So if the radiation output is like this from the source, এটার সাথে তুমি V lambda কে overlapping করাও, তারপর যতটা তুমি overlapping পাবে শুধু সেই পার্টটা we can see. So that is the total light output from the source. So this is the actual output from any light source. This is the actual light output from any source. এটা হচ্ছে আমার চোখের নেচার, তাহলে আমি only this part is useful. Okay, এবার যে ল্যাম্পের radiation will match with this V lambda nature, maximum part will fall under the visible part, that will be more energy efficient. We can utilize more amount of electrical energy, right? So this is from this light source we can use only a small amount of energy like this. Other than these are all wastage, right? So this is the radiant power or phi E. This is the V lambda function. This is the light output or phi V visible. Okay, input chilo P watt. Is this okay? So to calculate the visible part, we have to consider the V lambda function or the response hour I, the spectral and responsivity function of human eye V lambda. What is luminous flux? This is called phi, only phi, or you can also see phi V. This is the time rate of flux of total luminous energy responsible for visual sensation. The unit is lumen. Okay. So in this expression, what is this phi lambda? The output from any light source for each wavelength or spectral radiant flux phi lambda. You have to consider V lambda to compute the visible part. So the area under this total curve, এটাকে তুমি limit আছে lambda, মানে of course 380 to 780 হবে. So this phi V is this one. Is the part under the circle, is it clear to you? Then I will come to this km. ঠিক আছে না, মানে phi v হচ্ছে total radiant flux, total output. Phi v lambda is the output at each wavelength. So if you consider the phi phi e lambda with the visible part, you will get the visible light. এবার এর ইউনিট হচ্ছে ওয়াট, this is unitless. So you will get the luminous flux in watt. Now just to get the luminous flux in lumen, you have to compute with you have to multiply with km. Km is nothing but the maximum sensitivity of the photopic vision at 555, which is 683 lumen per watt. So my phi lambda was in watt. This is unitless. You multiply with km or lumen per watt. So now we will get the luminous flux in lumen. Okay. Ebar, if you want to compute the phi v in photopic region, you will get to compute the luminous flux in photopic region, we will get this expression. This is the luminous flux, or the amount of light we are getting from the source. It is 683, 380 to 780 nanometer is the limit, phi lambda, v lambda, d lambda. So this is my phi lambda. Eta hoche v lambda. So the total area under the curve, considering the v lambda, we will get this phi v. Okay. From phi lambda to phi v. This is phi v from the phi lambda. Any question? Anyone?
নো ম্যাম।
বাকিরা আর কেউ? বাকিদের কিছু কোশ্চেন নেই? Okay, যদি না থাকে, so next this is called photopic lumen, this is called scotopic lumen. Suppose a light is glowing at your house now, so how much light we are getting? Our C is perceiving some amount of light, but if you want to compute that light, either you can use the cone response or you can consider the rod response. So if you want to see the cone response or the photopic light, this is this amount, and this is the rod amount. So this is the photopic lumen, 683 phi lambda, v lambda, d lambda. This is the scotopic lumen, 1700 phi lambda, v dash lambda, d lambda. So here the value of km is 683 lumen per watt. Here the value of k dash time is 1700 lumen per watt. Okay. This is okay. This is nothing, just we have discussed this one earlier, the radiant flux and luminous flux. Radiant is the total considering the UV, considering the visible and the infrared. That is the radiant flux. But if you take only the visible part of the radiant flux, you will get the luminous flux. Okay. So phi E lambda is the spectral radiant flux. You consider V lambda along with that, you will get the visible part or spectral luminous flux. This is same, just instead of spectral, we are considering the total. So the total output phi E in watt, total visible output phi V in lumen. Okay. Now the luminous efficacy. So you know about efficiency. Efficiency of any system, how do you define efficiency of any system? As output by input, right? So luminous efficacy is also efficiency of any light source. We call it as efficacy. So luminous efficacy means how much light we are getting from the light to the total power that we are giving to that source. Efficiency is output by input, na? So again, here it is also output by input. So output we are getting light, the useful output rather. So total luminous flux output to the total input power. So the unit is lumen per watt. So how much lumen we are getting from watt? Okay, মানে 100 ওয়াটের বাল্ব থেকে যদি আমরা 800 lumen পাই, so the luminous efficacy of that bulb will be 8 lumen per watt. Okay, output by input. So কোনো lamp কতটা energy efficient or not, that we can understand by seeing the lamp efficacy. For example, the most energy inefficient lamp or the tungsten filament lamp, incandescent lamp, our efficacy is only 10 to 20 lumen per watt. For halogen, it's 15 to 25. For the CFL bulb that we use at our house, it's 55 to 80. The fluorescent tube, it's 60 to 105. For LED, it's 60 to 140. For metal halide, those are used in sports light, street lighting is 80 to 105. The lamp that are used in sports lighting, cricket field or football field or whatever, those are ceramic discharge metal halide, 90 to 105. For the yellow street lights, high pressure sodium vapor lamp, it's 65 to 140, and the maximum efficacy or most energy efficient lamp is low pressure sodium vapor lamp. This is 150 to 200 lumen per watt. Okay. So this is just an idea about the luminous efficacy over the years. So you can see nowadays, of course, the low pressure sodium vapor is not shown here. So nowadays we use LED in almost all the applications because it's more energy efficient as compared to the other fluorescent or halogen, mercury vapor, metal halide, etc. Okay, this is another white OLED panel. You know about the OLED TV, OLED screen. So here also the efficacy is very high. So now I will show the SPD that you have seen earlier. From there, can you tell me why the lamp efficacy is highest for low pressure sodium vapor? Just remember for incandescent it's minimum 10 to 20. বাকিগুলো সব মাঝামাঝি আছে. For low pressure sodium it's maximum 150 to 200. Can you tell me from this SPD? Can you explain? Anyone? Why is it maximum for low pressure sodium vapor 200 lumen per watt? আর এটার জন্য ছিল মিনিমাম, বাকিগুলো সব মাঝামাঝি. Can you explain?
অলমোস্ট মনোক্রোম্যাটিক।
হ্যাঁ, মনোক্রোম্যাটিক বলে মানে এনার্জি এফিসিয়েন্ট কেন? আর ওটাই বা এনার্জি ইনএফিসিয়েন্ট কেন? ফিলামেন্ট ল্যাম্প। এনিওয়ান? আরে কিছু তো বলো কেউ, মানে ঠিক হতেই হবে কোনো মানে নেই না? কি বাকিটা? জাস্ট আরেকবার দেখুন মানে maximum for low pressure sodium vapor 150 to 200 lumen per watt, minimum for incandescent lamp. Why? What do you think?
হ্যালো ম্যাম,
হ্যাঁ,
এনার্জি যখন বললেন তখন তো তার সাথে হিটের একটা সম্পর্ক থাকতে পারে, তো এটা অল ওভার কালারে হিটটা রিলিজ করছে বলা যেতে পারে, কারণ এটা একটা মনোক্রোম্যাটিকে অল্প হিট রিলিজ করছে, আর এখানে বিভিন্ন কালারের ভিজুয়াল রে পাচ্ছি বলে আমরা বেশি হিট রিলিজ করার জন্য।
না আমি আরেকবার বলছি তোমাদের রিজনটা কি হতে পারে। জাস্ট একটু আগে আমি বললাম যে this is the radiation output from a source. You have to consider the V lambda along with that. Only that part is useful. Baki partটা wastage. So we have to consider the radiation output as well as the V lambda. Then you can compute the total useful part or the light output part. Okay, now tell me.
ম্যাম এটার সাথে ভি ল্যামডাটাকে মানে মাল্টিপ্লাই করলে একই আসবে কার্ভটা অলমোস্ট, কারণ কি ভি ল্যামডার যে রিজিয়নটা আর এটার যেহেতু ইয়েলো লাইট ওয়েভলেন্থের পার্টটা সেম, তাই জন্য এটা বেশি।
To be more precise, the reason is that for low pressure sodium vapor lamp, the total amount of radiation is around this 600 nanometer, okay, in the visible range. So the total amount of output is in the visible region. So you can utilize the maximum output. Whereas if you see the tungsten filament lamp, I can show you one SPD. You can see the chrome, right? Chrome here. দেখতে পাচ্ছ না?
Yes, ma'am.
So if you see this one, you can see there's a small amount of UV and a lot heat is present here. Maximum amount of is IR. This is the total amount of output. The total output is distributed in the UV region also and in the IR region also. So the IR part is totally wasted, right? So you can utilize only the small part here. The peak value is in the IR region, right? Which is not visible. So that part is wastage. Whereas if you see the SPD of the low pressure sodium vapor lamp, the total amount of output is in the visible region. So we can utilize the maximum energy. For the other lamps, mercury fluorescent, sodium vapor metal halide, only we can perceive which is in the visible part from 380 to 780. মানে below 380 বা 780 তে radiation হয়তো লাভ নেই, you cannot utilize that part. So কম amount of electrical power দিয়ে তুমি বেশি output পেতে পারো. So that's why the low pressure sodium vapor lamp is more energy efficient. Whereas for the tungsten filament lamp, the maximum amount of energy is getting wasted in forms of infrared, in form of heat. So that's why that is the wastage of the electrical energy. That's why its energy efficient is low. It's not energy efficient. বোঝাতে পেরেছি?
Yes, ma'am.
Okay. So from this table, you can understand that here maximum amount of radiation is in the visible, here minimum amount of is in the visible range. For all the others, it's in between. Next is illuminance. So this is another important parameter. This is that luminous flux per unit area of a surface is known as illuminance. So whatever be the total light output at your room, you can utilize only which is falling over your table or which is falling over your work surface. So that parameter is the illuminance. For example, from this lamp, we are getting certain amount of lumen. But if we want to calculate the received light at any surface, then we can use the term illuminance. This is the luminous flux per unit area. So whatever be the total amount of light put from the lamp, the total entire light is not coming to my laptop or not coming to my table. So what amount of light I am getting on my table near my laptop, so then we can use the term illuminance. This is the received luminous flux per unit area. Lumen per meter square. So here it's 1 lumen per 1 meter square. So it's 1 lux. Okay. If you calculate in FPS, so 1 lumen per 1 feet square, that is called foot candela. So 1 foot candela is 10.76 lux. So for example, at your table, it may be 100 to 300 to 500 lux depending upon the light at your room. Near the window, it's 2500 lux. At outside, near the shade, is 5000 lux. Here it's 1 lakh lux. Okay. Here it is 10,000 lux, like that. So in the inside, it's somewhere 100 to 300, 400 lux, like that. So what is the radiant parameter as compared to illuminance? We call is irradiance. And what is the total amount of radiation falling over of your work surface? That is the irradiance. UV plus light plus IR, that is irradiance. And the unit is watt per meter square. For light, it lumen per meter square or lux. Spectral illuminance, lux per nanometer. Spectral irradiance, watt per meter square per nanometer. Okay. What's the time? Okay, so today it's up to illuminance and irradiance. So any question? Anyone? Can you, can any one of you can explain this expression, EV? Anyone?
রেডিয়েশনের সঙ্গে সারফেস এরিয়া গুণ করলে এনার্জি পাওয়া যায়।
হ্যাঁ মানে this is irradiance, spectral irradiance, E lambda total radiation out of the, I mean you have to consider the visible part. So this will be in watt per meter square. You multiply with the km lumen per watt, so you will get EV in lux. And so watt per meter square, lumen into watt per meter square, so it will be lumen per meter square or lux. Okay, this is EV lambda, so integration over this limit you will get the sorry, illuminance. Okay, so any question up to this? বাকিরা কেউ? কার কিছু কোশ্চেন নেই তো? Yes or no? রূপলেখা, সুস্মিত আছো এখানে?
Yes, ma'am.
You don't have any question?
No, ma'am.
Okay, fine. Okay, so can I stop the presentation now?